same data sets. Hopefully this will, no.
There it is.
There we go.
It's a little late, but you made it.
Make sure to get that frozen. We're going to focus on two major things today. We're going to talk about one of them is root mean squared error for determining the goodness of model fits. So both QQ-plot and so QQ-plot, remember, allows you to identify the shape of your Y variable. So you can determine, is it normally distributed? Because remember, you want your data to be as normally distributed as possible. Otherwise, regression analysis is highly suspect. It's still not bad, but the fit is going to not be as representative of what you want it to be. But so far, what the stuff we've done hasn't given you an idea of comparing models to each other. So we're going to get into that in detail today with two very common techniques. One is root mean squared error, and the other is what's called VIF, which is called variance inflation factor. Variance inflation factor sounds like a lot. It is actually an extension of stuff you've already done. So hopefully it'll include itself very well to what you're trying to do. So let me use over here. So we're gonna. This will be due by 10:15 today. So. And this is going to be homework number 5. This is VIF and REMS. Okay. So you'll see that, so you'll upload this when we're done. Okay, so we're going to learn about two things today with this data set. Let me unfreeze this. Oh, let me close that. Good news is I'm not showing anything that's. Okay. So first thing we're going to talk about is root mean squared error. So root mean squared error. So let's say I run R squared analysis on two data sets. And I get, so for this example, on two models. So two models, and you're trying to determine which one is the right one. And I get, and let's say adjust R squared, because there is never a reason not to use adjusted R squared. If you're dealing with a single x, a single y, single x, it's going to be really close to your R squared. If you're not, you have to use adjusted R squared anyway, so just use adjusted R squared. This is a good rule of thumb. And so you get your R squared, or start again, adjusted R squared. So for model number 1, you get 0.9438. And for number 2, you get 0.9417. Statistically, does this look better than this? I mean, technically, yes, but within error, I would not consider those two models to be really that different from each other. Our square root of 0.94, really, once you get past the second digit, it's just hand waving at that point. So, as a rule of thumb, look at those first 2 digits, and everything past that, ignore it. Because you're splitting hairs trying to justify the difference in accuracy at that point. And so that's a good rule of thumb. So these are, as far as I'm concerned from an R-squared perspective, identical. So how do I take which one? Well, this is where you get into RMSE. Let me put that up here so that I don't have to keep referencing the whole thing. RMSE is a calculation of the average size of each error. Because one of them could have slightly inflated behaviors over the other based on their deviation from the model. So it's a real simple calculation. RMSE equals the square root of 1 over n times the summation of I equals 1 to n of yi minus yi hat squared. So, actual minus model. So it's a residual term, squaring it, then divided by 1 over n, taking the square root of it. What that does, it gives you the root mean square value, which is a way of taking, it's sort of like an average, but it's a multiplicative average, not an addition-based average. And it allows you to see, on average, how close they are. So, if you have more noise in your data, you can actually get the same R squares if they track well on it. But it may turn out that one of them, the average error is much smaller than it is on the other one. So, smaller RMSE is better. So if you have R squareds that are close or even technically the same, it's worth doing this analysis. Because it's very possible that this one may have an RMSE, so let's look at their RMSE values. This one has a value of 10.47, and this one has a value of 4.13. All of a sudden, I'm like, this R squared technically slightly better. This RMSE tells me this is a much better value. So always use multiple criteria when you're determining the goodness of a model. It's often these will line up, but every now and then you're going to get ones that don't, and this is a good way to differentiate them. Now, if this came back as like 10.47, this came out back as like 9.83 or something, you can still go either way on these, and it's perfectly fine. Because at that point, this one's saying it's marginally better in one, this one's saying it's marginally better in the other. But this is a significant difference, so you're like, let's take that. And also look at this compared to your actual Y. So like this is 10.47 out of, and your Y values range from like 10,000 to 100,000, for instance. That's 10 out of 10,000 or 10 out of 100,000. That's 0.1 to 0.01%. That's a tiny difference. These are on the same order. But if this ranges from like 20 to 40, all of a sudden, this is a 25 to 50% error versus a, 10 to 20% error. So this is a far better option at that point. So also look at how they compare to the actual values, because they're gonna have the same units. Your RSME is gonna have the same units as your data. So always use that comparison. You can even normalize if you want by dividing by the mean and get a normalized value. That actually works too, but this is just a way of doing it. So rule of thumb is smaller RMSE is better. I'm going to put a note. Compare to magnitude of Y values. Because you may see something that's like, you could see something really weird, like this one returns, let's say 9.43, this one returns like 0.82 something, and you may go, well, this one's way better. And you look at our SMEs, and this is 10 versus 4 on values on average of 10. You're gonna go, yeah, this one, it fits better. This one has a lot less error on average. And what that means is this is probably being influenced by one data point. So this is where a leverage point can drastically influence it, because a leverage point is so far out that if it's off the line, it's usually off the line by more. And so it's going to shift your RSME, and it's gonna make your model move and fit worse, all because that one data point's influencing it. And this allows you to see when that's happening, because you're gonna see weird behaviors. If they line up where they're close to the same, or the one that's slightly better here, slightly better here, then you know that they're actually, the error looks good. But when you have those weird where they're not in agreement, it tells you to dig into the data more. Maybe there's something weird happening. Does that make sense? This is a simple calculation, especially if you're doing residuals, and if you're using Excel residual function, it's gonna give you the table already, so you can just create the RSME in that table that it creates, or you can do it by yourself in calculations in Excel. So, because it's just residual squared divided by the number of observations, and then take the square root of that. Why do we square it and then take the square root? Primary reason is to change the signs. That's the real reason. Because if your errors bounce back and forth, negative to positive, one of them is going to have a sum residual of close to 0. If the other ones are all really close to the line, but all slightly above it, it actually adjusts for that, where one of your models is shifted above or below, while the other one runs down the middle. What's the question on this?
Oh, you're just asking what the note was saying.
Oh, notice that compare the magnitude of your RMSE to the Y values, and make sure that you're not you don't want to give too much weight to RMSE, if at all possible. Meaning if you see this difference of where this is twice as much, but they're like I said, they're on data like 10,000 is the mean. Don't give it that much weight, because those are on the same order of magnitude. If you divide them out, they're both very small numbers. But if they're on the same order as this, like 10 versus 10 and 4 versus 10, now 100% error versus 40% error, that's a drastic difference. So make sure you give it the proper weight. Everyone comfortable with this? This is just kind of a quick thing. We're going to do this, or when we develop more models, we're going to start doing this calculation. There's really not anything to do with this right now, because we haven't done a model regression. I just want to get you the pieces to know what we're doing. Because right now, we're still trying to determine how to test our models when we have them. Because you can do some simple models, like you guys can do linear, like multilinear regression really easy. You can even determine whether there should be second order, stuff like that. We learned how to adjust for Y based on the QQ plots to make it. So we're really identifying piecewise, how do we build that model out for our data? Right now, what we're talking about with the model development goes away. In the first part of the class, we said we know what the structure of the data is. It's kinetic data, so it should look like this. It's heat transfer data, so it should look like this. Now we're getting into I got a bunch of data, I don't know what it looks like the data you have that you're selecting for your projects. And some of you, I had to have you select a different data set, like I went lower on your list, because some of them were like Python imports that didn't map the data well. And I'm like, I don't even know what they're trying to tell you here. So I tried to it's like your second or third one actually looks good, so let's go with that one. But hopefully you'll see all those up there. Now we're getting into models where you don't know. Is this still frozen? Oh, yeah, of course it is. There we go. You don't know what your model's going to look like. And so now we're trying to identify A, your initial guess model, B, as you make adjustments, how do you decide whether that adjustment was better or worse? So the next thing we're going to talk about is variance, inflation, factor. Okay, so to get you thinking about this, let me come up with an example. Actually, we've already talked about this. So let's say you have a tank, and you collect the volume in the tank, or actually, let's see, pressure at height equals 0, so the bottom. and you're also collecting the level data for the tank. Are these two things independent variables?
No.
No. Why?
The level's gonna, the higher the level, the more pressure that's up.
Absolutely.
Yes.
It's yeah, no, that's exactly it. You're talking about like the head, like you're
Yeah.
talking about pump head. The height, that height increases, the weight of the liquid increases, the pressure that it sees at the bottom of that is an increase. But it's not uncommon to see something like this done. But they're truly not independent. The question is, how not independent are they? Well, that's the feeling, but the challenge we run into is, what if your process is hooked up to other things downstream that could be influencing that pressure? This is where the challenge comes. In a direct isolated tank, we can actually write the equation that explains this. And it's really easy to do, because height is directly proportional to pressure, because you're assuming your volume doesn't change as it goes up, or your diameter doesn't change as it goes up. Your height directly changes your volume, which directly changes your weight, which directly changes your pressure. But that's not always true. Sometimes you have other influences there, like maybe the top of that tank feeds light components to another process for condensation or cracking or something that we don't know, like that's going to cause a draw off the top of the tank also, which is going to affect that pressure. So what you have to do is this guy, variance inflation factor, VIF. And what it does is it looks at your data and says, yeah, it's correlated, or there's multi-collinearity between, or collinearity between two independent variables, but how much? What is my collinear amount? And the way you do this, I actually love this. So we're going to say the steps to do this, and then we're going to do this with our data. Steps. Step one. Regress xi, so this is some predictor, in your list, versus all other predictors. So you're going to do a linear regression of that predictor with all other predictors. So let's say you do x, let's say you have 10, so we're going to do x1 as our independent variable, as our dependent variable now, and we're going to say do x2 through x10 predict you. So we're going to do a linear regression, x1 to the other ones. Then we're going to do x2, and we're going to regress you versus x1, 3, 4, 5, 6, 7, 8, 9, 10. And we just keep doing that piecewise. Take each piece out, call it the dependent variable, treat all the other x's as independent variables, and do the regression. So that's the first step. When you do this, you're going to record your adjusted R squared. For each one of these, you're just going to collect those. And you're going to save it off and say, this is my adjusted R squared for x1 in my VIF. This is my adjusted R squared for x2 in my VIF. And you're just going to get a table of R squareds based on the data set you're now calling the dependent variable that you pulled out of your independent. Now, at this point, you're completely ignoring your actual dependent variable. The y, you're not even dealing with it right now. Right now, you're trying to say, what in my x data can I actually use? Because one of the first mistakes people make with their regressive models, they throw everything in it, not realizing that there are variables influencing each other. So let's identify the ones that are influencing each other. Let's identify the ones that are influencing each other too much, and then let's get rid of them as fast as we can. Now, calculate your VIFs plural. So, for instance, if I'm looking at x1, I'm going to say VIF, and I'm going to use the subscript x1, just so you guys know I'm talking about x1, but I could do just VIF1 or whatever you want to do, equals 1 over 1 minus the R squared. Now, let me ask you this. How does this work if I have 10 x's that I'm looking at? So let's say I am looking at height, pressure, and I'm looking at like feed flow rate, I'm looking at composition of the feed, I'm looking at things that shouldn't affect these. Why does this work? Because if I linearly regress this, what's gonna happen? The coefficient, let's say I say, I'm looking at pressure versus all the other ones. My coefficient for level versus pressure is gonna be 1. And then all the rest are gonna be close to 0, very likely. So it's going to basically create a model that says pressure is a direct function of level. And so it doesn't matter how many you have, if the coefficient is 0, they're gonna zero those out. So all you're really worried about is that R squared. You don't really care about what coefficients are influencing it, you care about that R squared. Because what you would know is, can UP be predicted by either a single variable in my set or a combination of the variables in my set? If you can, you are no longer independent. So what are the ranges for VIF? Well, what's the range for R squared? What's that? 0 to 1, right? So if it's 0, what's your VIF? Yep. Right? Everybody good with that? So 0 VIF of 1. What if your VIF is 1? 1 over 0, that's infinity, right? So is a high VF good or bad? Let me ask this, if an R squared of 1, what does that tell you about your data? It's a perfectly correlated set. In this case, it's bad data, because it's saying you're predicting this X perfectly by the other X's. That means that X is not independent. It is actually perfectly correlated to some subset of all the other data pieces combined. So now, this R squared is bad, and R squared of 1 is very bad here. Here, the other one we looked at is very good, but here it's like, oh crap, my X1 is predicted by X2 through 10 perfectly. And that gives me a VIF of infinity, or it'd probably be like one point something million, and that's very bad. So our values, as a rule of thumb, are VIF, and this is, again, these are rules of thumb. Less than 5, good. VIF between 5 and 10, we generally say moderate correlation, or moderate collinearity, or let's say not say moderate, let's say potential. Potential collinearity. Or multi-collinearity if you have multiple variables, so they put multi in there, just so. And then a VIF greater than 10, serious. What was that?
The series.
That was weird. And collinearity. So if you see a VIF of greater than 10, toss it. Like that variable is fully predicted by your other variables. What does a VIF of 10 mean from the perspective of R squared? So if VIF is 10, we move this over here, it's 10 minus 10 R squared equals 1. So you end up getting an R squared of 0.9. So 1 minus 0.9 is 0.1, 1 over 0.1 is 10. Does that make sense? Would you consider an R squared of 0.9 to be a good fit? Yeah, absolutely. In real data, 0.9 is a great fit, which is why that 10 is a problem. What that's telling you is that 90% of your variation is predicted by the other things. And we call this variance inflation factor because it now means that, let's say I find out my X1 has a VIF of 13. It means that that variable is influencing our Y because we're trying to build it into our model, but it's in turn being influenced by these other variables. So everything's getting extra input into our Y versus it being universally distributed. Because now if I'm using pressure and level to predict, and I say, well, my level has this, my pressure has this, if my level changes, my pressure goes up with it, it's now getting twice the effect of the impact of a change. And so it's not an accurate representation of how it's truly affecting the variable. Does that make sense? So this is gonna be really important with your data initially, is figure out what the relationship is. And when you're doing your data analysis on your data sets for your project, should be the first thing you do. Well, first thing you should do is if you need dummy variables, get those in there. But then once you do that, do this VIF analysis. Figure out, were there any variables that clearly look to be correlated to each other? And if they are, start tossing. If it's, my rule is, if it's between 5 and 10, I kind of let it hang around, unless it's like, well, let's say it's sitting around 8, and my next highest one is, you know, let's say 1, for the sake of argument. Or not 1, that would be perfect. The next highest one is like 2, 2.5. I'm gonna go, well, that's a big jump. But if I have like 8, 7.5, 6, 5, I'm gonna go ahead and keep them all. But if I have a distinct split in the data where these are all low, and then I jump to 8, 9, 9.5, I'm gonna be like, we're gonna toss those guys and see how it does. And then if it turns out I can't get a good model fit, I'll start introducing them one at a time. The lowest one, like the 8 first, then the 9, then the 9.5 until I get my model to fit well. So you always want to fit your model with the least data you have to. So do this first, eliminate ones you think are not good, and then feed them back into your model slowly, and add them to your model to see how they affect it. So let's do this. We've got this data set, the sample set here where we've got the different X's. So we're gonna go through this exercise. And I think, we're gonna verify this, but I think this will work, but I'm gonna see. I may be wrong. We may have to do it manually. Oh, we will have to do it manually, actually. So we're gonna just do them piecewise. So I'm gonna do, I'm gonna copy this. I'm gonna copy at the end. And we're gonna start with, this one is, we're gonna do VIF for X1. So we've got our X1 here by itself. So this works out well. So we go to,
Wait, how'd you copy the sheet?
yeah, you just copy it. That's what I did. You just go right click on it, go to move or copy, and then create copy as a check mark at the end, and say where you want to copy it to. And we'll move it there. Because we're going to be using the same data over and over again, so it's easier if we just make copies of it. Now, we're going to go to analyze, data analysis. And we're going to do a regression. We're going to treat it as a linear regression. Because if there's a relationship there between the X's, we should see it. Our Y, because right now we're seeing how X1 is correlated to the other one, so our X1 becomes our Y value. Our X's are the rest of our X's. So that. Hold down control shift. Yeah. Tell it you have labels. We're going to ask for a 95% confidence interval just because why not? I'm used to just adding residuals in the residual class, so we'll do it. And then I'm going to create a new sheet called VIF. This is just what I'm going to use, VIF X1 results. Oh, and you can even do normal probability plots on your Y's. If you don't want to do it manually, like we did, you can actually do it here. If you just highlight your Y's and do normal probability plots, will do it. That's from the class last time. So we're going to apply it. It's going to spit this out. I'm going to move this over here, and then we're going to look at this. So we're going to go, okay, let's look at these coefficients here, because that's really what you, and then, so we get the R squared, right? We get an R squared, just R squared of 0.857. 691, so I'm going to go ahead and calculate my VIF here. So let me do VIF equals 1 divided by 1 minus adjusted R squared. I got a VIF of 7. Not great. Would love to see that below 5. It means we maybe need to keep an eye on this one and make a decision on it. So now we're going to just do the rest. Exactly what we just did on this one. Everyone understand what we did on this one? Everyone get through it. is now we're gonna take time and just do the next 4. I'm gonna make a bunch of copies of this. So,
Make a bunch of copies of the sample data.
yeah, because we're gonna need it to do X2, X3, X4, and X5. So I'm just gonna go ahead and preemptively do the other 4 copies of it I need. Name, VIF, execute. Okay, once you have that, the one thing you're gonna have to do different here is because it's, I just, you may be able to do it by just selecting your data differently. I just like to just make myself feel better. I'm gonna take my X2, because this is my VIF X2 that I'm looking at. I'm gonna copy it over here, and I'm gonna delete that empty column, so that I have my X's together and my new Y separated. That way when I select the data, it's easier. So then we go data analysis, we're doing regression. Our Y input is that. Our X input is that. And actually, I need to fix that because I've selected the whole column and then freaked out. There we go. Keep all these the same. Here I'm going to just call it VIFX2 results. Okay, what is your first thing you notice here looking at the X2 results? That adjusted R squared, is that a good adjusted R squared or a bad one? It's really bad, right? But what does that mean for our VIF? Should be very good. So 1 divided by 1 minus our adjusted R squared. That's almost 1. That means that X2 data is fantastic. It is not remotely predicted by any other variable. So that immediately makes me start to question that 7 even more. So I'm like, if I have a data set that's this independent, that means I'm gonna stumble across another one that's going to be directly correlated to that piece of data. And then we're just gonna keep doing the same thing over and over again. Does this make sense? If you have questions, please let me know. I'm gonna keep going through 3, 4, and 5, that you can watch what I'm doing, and please build yours also in the process. If you have questions, stop me, I'll come by, look at what you're doing, help you figure it out. me know when y'all are done doing at least the different data sets. Let me say, anybody not done?
I still gotta do X5.
Okay, cool. If you have questions, just let me know. And those of you, if you're already done, you wanna, I just created a summary tab where I could see all my, GIS together, but it's just up to you.
We're selecting access at 1, 2, 3. If we should say access. The three regression. Yep, I don't know why I said it. One second, second.
Your X bar is just the one X you're getting your whatever it's called, yeah. And then your Wi-Fi is all the other X's. That's your nice.
So okay, so it's already marked as all its flaws, basically.
So this one's X5, and then you have to watch X1, 2, 3, 4.
Okay. What is X1 and X2 you have there?
I copied over so I can select them all at once. So what else are you-
What are you doing now?
Because of what I just saw in the data, we're gonna, I'm just gonna plot them so we can see the behavior. Okay, everybody get all the data sets done? Okay, so if we look at the VF, the summary data, anything you need to wait?
Do you want us to like, graph the?
Oh, well, we're gonna talk about that in a minute. This is more just understanding the VIF. So if we look at the VIF data, it becomes really obvious, right? 2, 3, and 5 look fantastic, right? They are really close to 1, which tells me they are independent of each other, completely independent. What it's looking at is how well does the variation of this variable, how well is the variation of this variable predicted by these other ones? And they are not predicted at all. I mean, functionally 0. These two stand out, right? Now, what's nice about this is because you only have two data sets that have VIFs that are high, that tells you that they're predicting each other, right? They're not really being predicted by these other ones. Because when I looked at 2 by itself, I have those 2 in there, and it's not like any of these are very high, they're all very close to 1, which means 2 and 4, or 1 and 4 are not predicting the other variables at all, and the other variables are not influencing those other variables. So, that means we have 2, do we get rid of both of these? What was that? Absolutely not. Why would I not get rid of both? Because any one of them by themselves actually is a nice data set. It's not influencing the other variables around it. So if I kept 4, I can see that 2, 3, and 5 are not influenced by it. Or if I keep 1, I can see 2, 3, and 5 are not influenced by it. So I'm gonna pick 1 to keep and get rid of the other one. And if I do that, I would probably get rid of data set 1. Because it has a slightly higher VIF. It's not much, but I would just if I had to pick, I'd pick it that way. And that, now I've eliminated 20% of my data as unreliable, just with this quick test. And if we look, and this is why I did this, we saw from this information that fit, that there was something related to there, and as soon as I plot them, do they look like they're correlated? That looks really linear, right? And if I introduce, let's put my slope and intercept, make sure you don't select the why did I say that? Oh yeah, don't select the header, or else it'll throw you off. There we go. And if we get right here and we look, lo and behold, why is this so slow? But you can see, I always put 0.85 between two data sets. Oh, they moved. There we go. That's pretty well correlated. And so you can see it really easily here that there is definitely a collinearity between these two data sets. And so this is just a nice way to check it and go, okay, did my VIFs make sense? Because if it's between 5 and 10 like this, and I have two that I compare like that, go ahead and plot them. Because it's like, it could be a problem, and then when you plot it and see this, you go, definitely a problem, get rid of one. Does this make sense? You're gonna be doing this as the first thing in your data sets. After, let's say, first thing is going to be, if you need to put dummy variables in, put in dummy variables. Second thing is this analysis. What variables can I trust, and what variables are influencing other variables? Because in this example, we're talking about pressure and level, it was obvious. We understood that relationship. But like the data you guys have selected, you may not know the governing equations behind them, or there may not even be one. And so you need to identify those behaviors. And so this is what you're gonna do. Okay. Everyone comfortable with this? Can you do this on your project? Okay, so everybody take your data sets. The homework should be open. Go ahead and upload them. What you've done in Excel. And then we're gonna do an outside of class homework that's going to be, get your data sets, get them into Excel, and then you're gonna perform this analysis on your data sets. This VIF analysis. To identify what are your important variables. You may find that all your data points are independent, and it's not a big deal. But you may also find there's a correlation between this and like if you have data that has height and weight as data they collected for people, they're going to be correlated. The question is, are they going to be correlated enough that I have to ditch one of these? And very likely they are, because as people get taller, they are just in likelihood going to be heavier just statistically. So that's something to keep in mind. Any questions about this?
Why did you say you would choose X1?
Just because it has a slightly worse
So you would get rid of X1?
Yeah, that's the only reason. Like it's like 7.0 something, like 6.94. It's a toss up. There's no, once you have like paired data like that where their VIFs are basically equivalent, you can toss either one. Don't toss both. If all your other evidence picks that they don't influence the other variables. So like this one, we didn't toss both because there was no indication in the other variables that they were influencing it. If I had seen like multiple data, like if I had 20 pieces of data and 10 of them were showing me these values, I probably can't pair them off like that, so I'm probably gonna throw all of them out because I don't know how they interact. Like this one, I could directly say, it must be these two influencing each other because they're the only ones with high VIFs. Now what I could have is like 20 data sets, and I say I have 5 that are like 7 point something to 9 point something, and then the other ones are like 2.3, 3.1, 1.7. What's happening is all of those are being influenced by those as individuals, but in small pieces. Here, all the influence was between two variables, but the other ones are gonna be, this one can be fit by these 5. And when you run into those, you may have to ditch all the high VIFs at that point. Only if you compare them and see this type of behavior, where it's clearly one is influencing the other directly, can you toss only one. So if we had plotted this, and we hadn't seen this, we saw like a scatter, it would mean that it's some small combination of the other variables are predicting both, and then we throw out both. But because we could see directly what the influencer was, we throw it out.
We submitted in Blackboard after like you got a Blackboard.
What's that?
Submitted.
Yeah, submit it on Blackboard. So there's a homework, listed homework number 5 for today, just uploaded for today. And then and I'll put an active homework up that will be due, probably not before next class, I think that's gonna be pretty quick, probably by Monday, to just go through and do the DIF on your data. Which means you'll get with your group, and if you have to do a dummy variable creation, that's the step you're gonna have to do. Okay? Maybe I'll do it next Wednesday to give you guys over the weekend, and if you have questions Monday, you can ask them how to do Wednesday, or you do the DIF. And so this is, we're now getting into identifying, like how do you identify the data fit, how do you determine whether it's a good model. Then we're going to do a straight linear regression of this data we have. So we're gonna keep playing with this data set. And we're gonna try different models, and then we're gonna compare models using the techniques we talked about to pick which we think is the best one. And so then as you learn the techniques on this data set, you can apply it to your data set and just keep refining it until you're like, I trust this model. This is the best model I can come up with. It doesn't mean that you're gonna get a great model, because sometimes your data just doesn't fit the variables you collected. That's the reality of it. But we're gonna find the best model you can get for the data you have. And then you can make goodness decisions on, is this a good model, is it predictive? Or do I need other information that I don't have? And this is something you have to do in industry where they're like, hey, here's our data, can you predict this? And you may come back and say, yes, I can, or you go, no, I can't. I really need, maybe intuitively, like I need this other data that you haven't given me, or we haven't been collecting. And so then you start playing with that. Let's see, what else are we talking about? We're gonna learn 2 other techniques for busy model, like goodness of models, called AIC and BIC. We're gonna learn those next time. And then we're going to basically lay out what your entire criteria are for selecting your models. Once you do this to your data set, then it's just a brute force approach. It's test a model, look at the regression, look at the shapes. Is there something there I can identify? Is there a way I need to change my model to fit that? You're going to do this DIF, then the next thing you're going to do is going to be QQ plots on your dependent variable to determine whether you need to transform it to make it normally distributed from a non-normal distribution. Then you're going to start fitting models and testing the models, comparing them to each other. Basically, it becomes a death match between your models, where you compete them against each other until you get to the best one. And the best one may not even be a good model. That's the reality of it. The best one may be, based on the data I have, this is the best I can do. Okay? Any questions? Cool. Then get with your group, and for next time, we'll start going into some more stuff. So we're going to play with this next time. We're going to do regression analysis on it and test the goodness. And I'm going to show you 2 more techniques.
When did you say the homework was due?
The homework is going to be next Wednesday for your data set. I'll post that this afternoon.
Okay.
With all the data. And for that, you're just going to be making sure you do this.
Okay.
Actually, we may do 2 pieces. We may have you do this and do the QQ plot. Because one's looking at the Y, one's looking at the X. You're basically cleaning up the 2 halves of your data, your dependent variable and then your independent variables. And now you've got this clean and you're happy with them. Now we move forward with model development.
Hold up. You gotta go work?
We got lab ones there, or today, right?
Yeah.
We have lab today.
Yeah.
You're gonna be late today now.
I'm here now. I didn't see that top of it at all.
Oh yeah, we're gonna come to a meeting for a
No, yeah, but it's gonna be.
Yeah.
We're meeting
About an
here.
hour.
I see young and yeah, like, get out of here, bro.
I gotta get food.
Get my shoes.
Ignore my pop-up, sorry, I get so many emails. Oh, you got a painting in your backpack?
My mom and me as a baby.
Alright, run back, take a look.
Don't make fun how bad I was.
Oh, come on now. That's a chubby baby too. Oh, cute. But your mom's stunning. Look at her. Yes. She is curvy. Look at her. She's sitting there like popping her head. Oh, that's so cute.
She wants me to get it like reframed or something.
That is so, you need to go Hobby Lobby. They have really good framing there. I love that. I'm gonna put that in there.
What's up, bro? The meeting?
Ryan's busy right now. He's
What are you doing?
on duty. You need to get an appointment with him, sir.
What is he doing?
He's helping me fix my computer's doing some weird.
You wanna check the office?
No, give me a few minutes before we
Hey.
go, please.
Hey, Cassandra, did you figure it out?
12:15.
It doesn't load for me.
Huh?
It doesn't load for me.
Let me see. I like it out.
Oh, thank you. Where's that? Is it Nova?
They both went to wait for a doctor in school.
So,
Yeah.
crossing on asking, and I tried it, but it doesn't work for me.
Is it that little like green tab?
My son's never doing it.
At all, and it's all.
Or you can just write
The isobutane tower. It's gonna be out, it won't split, it will not split, it's like refusing to.
Where do you put
And so, he should help with that, it's his job. But he didn't come here yesterday, like he came in, he talked to me building, he was really nice, and we're like, what the heck?
I don't want him to talk to you right now because it would really
It was bad. The only place I got sunburn was my shoulders. That's it. I don't know how either. I know she's very expensive.
Oh, did you? What's this?